Hi, I'm James, and I'll be presenting this work, Indistinguishability Obfuscation of Null Quantum Circuits and Applications, which is joint work with Giulio Malavolta. So first, I'll share some background on the notion of indistinguishability obfuscation, or IO, for classical circuits. So an obfuscator is a compiler that takes as input a description of a computer program. So for now, think of it as a classical program, and outputs an obfuscated program. And so the point of obfuscation is to scramble a program to hide its implementation details while maintaining the functionality of the program. Okay, and so the security of IO says that for any two programs, P1 and P2, that compute the same functionality, their obfuscations should be computationally indistinguishable. Okay, and this notion has been extremely well studied over the past decade now in the world of classical cryptography, and it's even been dubbed a central hub of cryptography because of all of its applications. And so we can quickly see just the sheer number of applications that obfuscation or IO has in the classical setting, including fully homomorphic encryption, witness encryption, multi-party non-interactive key exchange, and the list goes on and on. And also over the past 10 years, there's been a huge amount of work on constructions of classical obfuscation, starting with some initial candidate constructions that showed basically the plausibility of IO for general circuits. There's been a whole line of research constructing IO by going through the functional encryption route. And today, the state of the art is that, well, we know how to construct obfuscation for all classical circuits from well-founded assumptions. Including assumptions on bilinear maps, which are not post-quantum. So there's also another line of work that has also been focusing recently on building post-quantum obfuscation, and we have some good heuristic candidates for that. Okay. So this talk is going to be about the notion of quantum obfuscation, which is a natural extension to considering quantum programs, right? So now let's say Q is some quantum program. It could be a unitary or more generally a quantum circuit. We'd like to, well, we're wondering if we can obfuscate it, okay? And there's been much less work on the notion of quantum obfuscation, okay? A few works recently have studied just some definitions and some impossibilities. So putting forth different definitions of quantum obfuscation, showing that some of them are impossible. Okay, but if we look at like a similar chart of like applications and constructions, it's much less well studied than the classical setting. In terms of applications, quantum indistinguishability obfuscation is known to imply this primitive called witness encryption for QMA, and I will actually define this later in the talk. And in terms of constructions, a few works have studied this. So a couple of works have looked at how to obfuscate, like basically perfectly obfuscate certain very limited classes of quantum functionalities. And so perfect obfuscation means that actually the obfuscated programs are perfectly indistinguishable from each other. But we can't hope to do like perfect obfuscation for all polynomial time quantum circuits. So we'll need to move to computational assumptions, and there has been a work that addresses this and shows how to obtain quantum IO for circuits with Clifford gates, plus a few like logarithmically many T-gates. So this is some class of circuits, quantum circuits, that we do know how to obfuscate, assuming classical IO. Okay, but this is pretty much all of the prior work on quantum obfuscation. Okay, and in fact, it's still open whether it's even possible to realize in this notion of indistinguishability obfuscation for all efficient quantum circuits, for general quantum circuits. So this is a question that was kind of, addressed in the classical setting around a decade ago in those first works that showed candidate constructions for classical obfuscation. This is still completely open in the quantum setting. In particular, we don't even have any candidate or heuristic constructions. We don't even know if we can obfuscate quantum circuits using ideal classical obfuscation, for example. Okay. So this is some background on classical IO and quantum IO. So our work is basically our results are split up into two parts. We have some results on the construction side and some results on the application side of quantum obfuscation. Okay, so first I'll describe the construction or our results here. So assuming the quantum hardness of learning with errors, which is a pretty standard post-quantum hardness assumption, along with a virtual black box obfuscator for classical circuits, we can show that there exists an obfuscator O that can be applied to quantum functionalities or general quantum circuits with the following properties. So for correctness, we show that the obfuscation roughly preserves the functionality of Q. So it's exactly the functionality of Q up to some negligible factors. And then for security, we can show that for any pair of quantum circuits Q1 and Q2, such that both Q1 and Q2 output 0 with overwhelming probability on every input, meaning these are both so-called null quantum circuits, that their obfuscations are computationally indistinguishable. And so this is exactly the quantum analog of a previously studied notion of null indistinguishability obfuscation in the classical setting. Okay. And before moving on, I wanted to highlight this assumption a little bit more. So in fact, it's actually been known for 20 years, at least in the classical setting, and there's been some recent works on this in the quantum setting, that it's impossible to, in general, construct a virtual black box obfuscator that satisfies VBB security for all classical circuits. But our construction that uses VBB obfuscation can be heuristically instantiated with an indistinguishably obfuscator for classical circuits that's post-quantum. And one could assume that the resulting construction is secure. Okay, because for one, these impossibility results only only hold for very specific contrived circuits. And this is similar to something you might do in the random oracle model. Since we know we can't, actually instantiate the random oracle model in the real world, what we do is we, replace the random oracle with a concrete hash function and assume security still holds. Okay. So the other thing I wanted to say about this assumption is that in the paper, we actually show also how to replace VBB obfuscation with classical IO, along with this new notion of what we call dual mode classical verification of quantum computation. Unfortunately, also, this is also this notion is something we also only have heuristic candidates for. So basically the bottom line is that what we give is a candidate or heuristic construction of indistinguishability obfuscation for a large class of quantum circuits, namely all null circuits. Okay. So this is our main construction. The second part of our results is on the application side. So like I just mentioned, this is what we construct, quantum null IO, and in fact, our obfuscated circuit actually has a classical description. Okay. And so we show that this implies witness encryption for QMA, also with a classical ciphertext. Okay. And then we show that witness encryption for QMA is actually a very useful notion. It has all of these applications, okay, including a non-attractive zero knowledge proof for QMA. And so we give basically the first candidate construction of this primitive in ISIC for QMA. We show how to construct a related notion of two-message witness indistinguishability for QMA. We show how to construct a attribute-based encryption scheme for a quantum complexity class BQP. Attribute-based encryption is this fine-grained notion of public key encryption that is very well studied in the classical setting, and we give the first candidate construction of it for a quantum complexity class. And we also have results on constrained PRFs for BQP and secret sharing for monotone QMA. And I should say, actually, a lot of these applications or implications also require just a classical indistinguishability obfuscator. Okay. But yeah, I will encourage you to, well, I'll refer to the paper for actually all of these descriptions of all these primitives and all these implications. For the rest of this talk, I just wanted to talk about first this implication, so quantum null IO implies witness encryption for QMA, and then give an overview of how we actually construct the quantum null IO. Okay. So first, witness encryption for QMA. So what is it? So let L be a language in QMA. A witness encryption scheme, the encryption algorithm takes as input a message M and an instance X, okay, and produces a ciphertext such that if X is in L, then any witness psi for X, so this is a quantum complexity class QMA, any witness psi for X can be used to decrypt the ciphertext and learn the message M. On the other hand, if X is not in the language, then basically the ciphertext completely hides M, in the sense that no efficient adversary can recover M from the ciphertext. Okay. So how do we construct such a scheme from quantum null I/O? Well, if we want to encrypt the message M under an instance X, we'll first define the circuit QMX to be the circuit that takes as input psi, and then outputs M if and only if psi is a witness for X. So what the circuit does is it just runs the QMA verification circuit over X and psi. If it accepts, it outputs M. If it rejects, it outputs, say, some bot symbol. Okay, and then the ciphertext is actually just going to be a null obfuscation of the circuit. Okay, and so why does this work? Well, so for correctness, the correctness of our null I/O directly implies the correctness of this witness encryption scheme, because, given a witness, you can run this obfuscated circuit, which will behave just like Q and output M if psi is actually a witness for X. And then security of the null I/O suffices to prove security of this witness encryption scheme, right? Because if X is not an L, then Q is actually a null circuit. Okay, so the security of the null obfuscator actually implies that M basically remains hidden in the ciphertext. Okay, so this is the implication, and this is just directly follows the classical, it's been known that basically classical null I/O implies witness encryption for NP. So this is kind of the quantum analog of that implication. Okay. So now I want to say about some words about how we actually build the quantum null I/O scheme. So it's not too complicated. We basically make use of just two tools. Okay. So the first is a two-message blind classical verification of quantum computation protocol, or CVQC. So what is this protocol? It's a protocol between a classical verifier who has some quantum circuit Q that would like to run, but it can't because it's classical. So it's going to interact with a quantum prover. Okay. And so the verifier will first run some gen algorithm to produce some public parameters. The prover will run some prove algorithm to output some proof pi. And the verifier will run some classical output algorithm on Q and pi to produce its output Y. Okay. And so we want to ensure some properties out of such a scheme. So one is blindness. The prover actually can't learn anything about Q from these public parameters. Okay. So the prover doesn't actually learn what circuit the verifier is interested in running. And the other is soundness, which means that, if we want to evaluate Q on X, then soundness says that the prover can't force the verifier to output a wrong output. Okay, so the verifier will always, accept with negligible probability output the correct output Y equals Q of X. Okay, and we can obtain such a scheme by combining. So in prior works, it was already known how to construct at least a heuristic construction in the random oracle model of a two-message CVQC, which CVQC was first constructed in this work of Mahadev, and then these follow-up works showed how to compress the round complexity. And then we can basically just run such a scheme under quantum fully homomorphic encryption, okay, to make it blind. So this is the first tool. The second tool is just an obfuscator for classical circuits, okay. So given these two tools, our construction is quite simple. So if we want to obfuscate the circuit Q, what we'll do is we'll just first run the verifier generation algorithm on Q to produce these public parameters. And then we'll output a classical obfuscated version of the verifier's output functionality. Okay, so this is actually the entire construction of quantum null I/O. It's just these public parameters and a classical obfuscation of this verifier's output functionality. To evaluate this, so say you have some input X, or actually in general, even X could be a quantum input as well. And you want to evaluate this obfuscation, you would just run the prover algorithm, the CVQC scheme, to produce your proof pi, input into the classical obfuscation to learn Y, which should be equal to Q of X. Okay. So yeah, this is how the scheme works. And now I just want to say a little bit about how intuitively why this is secure. Okay, so let's consider any null circuit Q. What we can say is that this classical obfuscation, or this classical oracle V out of Q, can be replaced with the all zeros oracle. So an oracle that just responds, just outputs 0 on every input. Okay, and so why is that? Well, any adversary that can distinguish these two oracles, we can use to actually break the soundness of the CVQC, right? Because any input that actually causes this oracle to output 1 is a proof that can be used to break the soundness of CVQC. Okay, right? So here we rely on soundness, and then finally, after we do this, after we replace this with the all zeros oracle, we can just note that these public parameters hide Q due to the blindness of the CVQC scheme. And so basically what we've shown is the two components of this null IO we've shown are, essentially like computationally independent of the underlying circuit Q. Okay, so this is roughly why our scheme is secure. Okay, so yeah, before I ended, I just wanted to talk about a couple of possible extensions or open problems suggested by this work. So first you could ask, okay, well, I just described why security holds for null circuits, but why are we stopping there? Why can't we use this, this paradigm to obfuscate, maybe all quantum circuits, or at least more quantum circuits than just null ones? Okay, so the issue is that if you think about the, the evaluator or the adversary in the quantum obfuscation game, they have access to the obfuscated verification circuit, which they can run multiple times, right? And so, in order to argue that this is secure, that they're not like learning anything about the underlying circuit, you'd have to use the fact that the underlying CVQC is actually reusably sound and blind, meaning that a cheating prover can basically query the verifier multiple times and still blindness and soundness holds. So unfortunately, we actually, at least for like non-null circuits, right, we actually show explicit attacks on the reusability of CVQC protocols. Okay, so this leads to a nice open question of whether we can actually construct CVQC protocols that are reusably sound and blind. Okay. And next you could ask, well, why do we need to rely on classical virtual black box obfuscation? Could we rely on the weaker notion of indistinguishability obfuscation? So here the issue is that the soundness of CVQC is not perfect. In fact, there will exist many, even exponentially many, like bad accepting proofs, even for like a null circuit, right? And the point is that a cheating prover just shouldn't be able to find one of these bad accepting proofs. But we need to use VVV obfuscation in order to extract such a bad proof from a cheating adversary to get the reduction to CVQC to go through. And it's not clear how to do this if we only relied on indistinguishability obfuscation. Okay, so this, these lead to these two open questions. First, can we obtain a candidate construction or Hirscher construction of IO for all quantum circuits? Okay, so this remains open. And next, can we obtain any of our results? So quantum null IO, witness encryption for QMA, NISIC for QMA, from just IO for classical circuits, plus maybe some other standard hardness assumptions. Okay. And that's all I wanted to say. So thank you for listening.